Today we'll be looking at current electricity. We'll be looking at current electricity. Previously we looked at the static electricity. We looked at static electricity, the electrical energy that is found in any atom. Okay, whether the atom is moving or is not moving, the electrical energy that is found in the atom. So today we'll be looking at the energy that is found in when charge travel from one place to another. Charge per unit seconds. Okay, is current. So what is current? We start by explaining the meaning of current. Current is the amount of charge that is passing through a point in a circuit. Okay, if you have electrical circuit, for example, if this is our electrical circuit, I have if we have electrical circuit, let's say we have a battery here, simple electrical circuit. Let's just have a simple electrical circuit. And then we have a bulb. We have a bulb here. We have, let's say we have a switch. This is a simple circuit. This is a simple electrical circuit. Okay? So when the switch is closed, then the current, this is the positive side of the battery. This is the positive terminal of the battery. This is the negative terminal. This shorthand is the negative terminal. And these positive ones are these tall ones are the positive terminal of the battery. Every battery has certain voltage or EMF. Let's say 12 volts. Let's say this battery can offer 12 volts. Okay? The battery, this is just the smallest way of representing a battery. A cell is just this. This is a cell. Okay? Most cells, they give 1.5 volts or 2 volts. 1.5 volts or 2 volts. So when you have one unit like this, it's called a cell. But when you have more than one, like starting from 2, is a battery. Okay? The battery could have up to 6 of this. It depends, okay? The battery could have up to 6 cells. So if this one is 2 volts, 2 volts, 2 volts, 2 volts, 2 volts, 2 volts, everything will be 12 volts. Okay, but this is the simplest way of representing a battery. This is the simplest way of representing a battery. So each cell either contribute 1.5 volts or 2 volts. So what you have is in textbook you see they write like this. They write one like this, and they put like something like small dot, and then before they draw another one. So what it means is that there are many cells here. Okay, we don't know depending on the value they give to the cell. It could be 6 volts. If it's 6 volts and they tell you one cell is 1.5 volts, if one cell is 1.5 volts, it means there are 4 cells that made it 6 volts, that made the battery 6 volts. Meaning there are 4 cells. Even if we write 2, does not mean it's actually 2 cells. Okay, so I hope that is clear enough. Now, when we close the switch, this is an open switch. Okay, switch is either open or closed. If the switch is like this, we say it's open. But a closed switch is like this. A closed switch is like this. This is a closed switch. This is a closed switch. Closed. Close. And this one is open. So when we open switch, current don't flow. Current don't flow because the switch is still open. is when the switch is open, we have this. So when the switch, when we close this one, it becomes this. So this is a closed switch. Current flows in a closed switch. When the switch is closed, that's when current starts to flow. Because there's a gap in this wire. When the switch is open, there's a gap. So once there's a gap, current cannot flow in the circuit. Current cannot flow in the circuit. So whenever we close the switch, like if you close it now, this place will be closed. Okay? It will look like this. So when that happens, the current starts to flow. But the current flows from the positive terminal towards the negative one. The current flows from the positive terminal towards the negative. So current flows in this direction. Current flows in this direction from the positive terminal towards the negative terminal. That's a conventional current. Okay, conventional current flows from the positive terminal towards the negative. But electron flows from the negative, to the positive. Electron flows from the negative towards the positive. Electron flows from the negative towards the positive. Okay? Electrons flow from the negative towards the positive. But conventional current flows from the positive towards the negative. So take note, this one's always been asked in Cambridge IGCSE. Okay? So we move on. So we say, whenever you have a circuit, okay, we say whenever we have a circuit, and if the circuit is closed, current flows. Now this current is actually a charge. Current is called a charge. Current is called a charge per unit time. Charge per unit time. This current, the symbol for current is I. Okay? I is the charge. Charge on the battery. Charge that is produced from the battery that travels in the wire of the circuit. The charge is from here. Is boosted the energy from here, the electromotive force. This is 12 volts. The electromotive force push this charge to start to move. This charge is here, actually. It's in the battery. So this charge is being pushed by the electromotive force, which we call the voltage. Okay, it pushes the charge to start to move. When the charge is moving, we call it a current. So anything that moves is per unit time, right? Anything that moves is per unit time. So when charge moves, we divide by the time it has taken to move, we call that current. Charge per unit time is called current. Q is the symbol for charge. Q is equal to charge. Q is equal to charge, or charge is Q. The symbol for charge is Q, and T is time. Per unit time, right? Time is being expended. As you move, time is being used up. Okay? Time is being used up. And I is the current. I is the current. So current is nothing but a charge in motion. Current is nothing but a charge in motion. So it's not like a new terminology such that we don't know what it means. It simply means a charge that is moving. Okay, when you study atom, you talk about electrons, okay, and the proton. We say the protons and the neutrons are found in the nucleus of the atom. The protons and the neutrons are found in the nucleus of the atom, while the electron revolves around the nucleus. The proton is the one that is positively charged. That positive charge is the charge we are talking about. That positive charge is the charge we are talking about. While the electron is the negative one that is moving in shell, that is revolving in shell. The electron is the negative one that is revolving in shell. That positive one that is dormant is called the proton. The proton is the charge that we're talking about. This charge is boosted with electromotive force from here and begin to push to move. When that charge moves, we call it current. When the charge moves, we call it current. So charge per unit time is called current. It's called what? Current. Okay. So we say the current is the amount of charge that's passing through a point in a circuit. So now we also know the meaning of a circuit. We show the circuit. We've drawn a circuit. We've drawn a simple circuit, a basic circuit. So the amount of charge that is passing per unit time is called current. If there is 5 coulomb charge passing, if there is 5 coulomb charge, the unit of charge is coulomb. The unit of charge is what? Coulomb. The unit. SI unit of charge is called coulomb. So please take note of that. And the SI unit of current, the SI unit of current is called ampere. So we say unit for charge is coulomb. So we need to know the physics, we need to know the units of physical quantity. Okay? Time, we already know the unit. Unit for time is second. Unit for time is seconds. We already know this, right? Then unit for current is ampere. So current, the unit is ampere. So when you see us, we solve any problem, we must put the unit. If you don't put unit, you will not get the mass. Okay? So unit for current is ampere. A-M-P-E-R-E. Ampere. This is the unit of current. Ampere. And the symbol, unit symbol, we also need to know each unit symbol. The unit symbol for this one is capital C. The unit symbol for this is S. And the unit symbol for this is capital A. So we need to know the unit and their unit symbols that are used in each of the physical quantities. So in physics, we must put unit in any physical quantity that we have determined. For example, if we say 5 coulomb charge, this is the amount of charge that is flowing in this circuit. So 5 coulomb charge flows in 2 seconds. What is the current in the circuit? What is the current? 5 coulomb of charge flows in this circuit for 2 seconds. What is the current? So all you need to do is to say current is the charge divided by the time it has taken to move around. The charge, the amount of charge divided by the time it has taken to move around, which is 5 divided by 5 coulomb divided by 2 seconds. Divided by 2 seconds. So if you put the basic unit, even if you don't know the real unit, you can use this primary unit. So 5 divided by 2, we get 2.5, right? So I get 2.5. We get 2.5 coulomb per second. 2.5 coulomb per second. 2.5 coulomb per second. Okay, we get 2.5 coulomb per second. We get 2.5 coulomb per second. Okay, so that what we just said is what we have here. Okay, we're putting it in a formula form, in a triangle form. So if we look at the triangle format for what we just said, if you look at the triangle format for what we just said, you agree that this has a pattern. Since you say current is charge over time. Charge over time. Current is charge over time. The amount of charge passes through a point per unit second. Amount of amount of charge passing through a port per unit second. So we say current is charge divided by time. Charge divided by time. So here we can derive three formulas from this triangle. We can derive three formulas. The first formula is for current. Current is charge over time. Current is charge over time. The second formula, we can call this equation 1. The second equation or second formula is that of charge. Now what is charge? Charge, if you take charge, you say is current times time. You multiply the two, this double sum, because they are being multiplied. If you are looking for charge, you say current multiplied by time. Say charge is our current multiplied by time. The third formula, this is the equation, or second equation. The third one is time. So you're looking for time, and you're giving charge, and you're giving current. So time is charge divided by current. Time is charge divided by current. Time divided by current. Charge divided by current. That's what time is. So we call this equation 3. Okay, so these are the three basic equations we need in case we need to calculate anything. Okay, let's move on. So we always say, since we know current is charge divided by this time by making current the subject. Okay, you make current the subject. Then you can say charge will be current times time. Charge will be current times time, which is Q equal to IT, which is what we have highlighted. We mentioned the unit. We saw although the unit of charge is coulomb, the unit of this is second. The unit of current is ampere, which can also be written as coulomb per second. If you look at here, we wrote coulomb per second. If you look at this place when we calculated for the current, we wrote coulomb per second. This coulomb per second is same as ampere. It's same as ampere. So I can simply write 2.5 ampere. I can write 2.5 ampere for the current. Because coulomb per second is same as ampere. It's same as ampere. And ampere is internationally acceptable. This one is okay even if you write coulomb per second. You're right. You're not wrong. Okay? So but it's just that the standard one is ampere. Okay, so we have defined the quantity. I've already told you what Q stands for. Is charge, which is measured in coulomb, as the unit is coulomb, and I stands for current, which is measured in ampere, which is capital A. Now here is the triangle for the formula which demonstrated already. We say this current, which is symbol I, is the charge, symbol Q, divided by time, symbol T. And if you're looking for time, is charge divided by current. And if you look for charge, you say current times time. Current times time if you're looking for charge. So we already know how to apply this type of triangle. So let's look at direct and alternating current. What do we mean by direct current? What do we mean by alternating current? Because we use this more often. So when two oppositely charged conductors are connected together by a length of wire, charge will flow between the two conductors, right? So if I have a plate with a positive charge and another plate with a negative charge, but I use a wire, a connecting wire, a conductor, to connect these two plates, what will happen? Charge will flow between these two plates. Charge will flow between these two conductors, right? So there will be flow of charge. Now, this flow of charge is called electric current. When charge is flowing, this is what we call electric current. The greater the flow of charge, the greater the electric current. The more charge flow between these two conductors, the more the electric current that we have, or the more electric current that is produced. Now let's talk about electric current in two ways. Okay, let's talk about electric current in two ways. There are two types of electric current. One is called the direct current, and the other one is called the alternating current. Current can be direct current, that's DC. Direct current means DC current. Okay, and alternating current means AC current. Current can be direct current or it can be alternating current. Now let's take a look at direct current, and let's take a look at alternating current. Is that okay? So when we write current, we can divide it into two. When we write current, electric current, we can divide it into two. We can divide it into two. One is direct current, and the other one is alternating current. So I'll just write DC. You already know what DC is, direct current. And then an AC, alternating current. Now, how do they look? How do they look, and how do we differentiate them? Now, let's take a look at direct current. For direct current, if I plot the graph for a direct current, it will just have one voltage value. Let's say here, at this point, we just have, maybe if here is 10 volts, it will just be 10 volts to be constant throughout. 10 volts will be constant. This is the time as this is the voltage as this, or current as this. Or 10 ampere, for example. Let's say 10 ampere. Let's use current. Okay, this is the current as this. If you plot it, it will just be one value throughout. The value is constant. The value does not change. This value does not change, does not fluctuate. Does not fluctuate. So it just says direct. If it's a positive value, just like positive 10 ampere. Okay, that's a direct current. But what about AC current? Alternating current varies. It varies. Okay, it does not stay with one value. It varies. Maybe it to be like this. It becomes another way. Okay, it will be like this, and it will also be just like this. Maybe let me use another. Let's use another color. It will just be only like this. Maybe if it's only the positive one, values like this. If it does not have the negative side, it will just be like this. Okay, so it's alternating, it's changing. The value goes up, come down, go up, come down. It's changing. It's not constant. It's not fixed. It's not fixed. Okay, that's what we call alternating current. The value is not fixed. The value is not there, fixed. You see, the value changes. It will also vary up and down. So in such a way that it has negative value and positive value. It will also go to this extent. Alternating current will also be written like this, such that we have positive and negative value for it. For example, it could be like this. See, this is the positive side, and then we go to the negative, like a sine wave. Like a sinusoidal wave. Okay, positive arm, then negative arm. Okay, this is alternating current, meaning it's changing. Okay, it's not fixed. It doesn't have a fixed value. This is alternating current. This is the negative side of the graph. This is the negative side, and this is the positive side, positive current side. So if here is plus 10, this value varies up to negative 10. Vary up to negative 10 ampere or volts, depending on what we are plotting. Okay, so this is the alternating current. We call this AC current. A current that changes. We call it alternating, changing. Alternating is changing current. Current that is not fixed, does not have a fixed value, it fluctuates between given set of values. Okay, this is an AC current, while this is a DC current, while this is a DC current. Is that okay? So let's move on. Now we know the difference between these two currents. Now direct current is produced when using like dry batteries, when using batteries or cells. Anytime you use battery to build your circuit, you're producing a direct current. Okay? So a direct current is produced when you're using dry cells and batteries, and sometimes generators. Although these are usually AC, generators are usually AC current. Okay, generators are usually AC current. The electrons flow in one direction only, from the negative terminal to the positive terminal. We already showed this at the beginning. The electrons flow from the negative to the positive. But conventional current, they flow from the positive to the negative. We've already showed this from the beginning of the lesson, right? When we drew the circuit, when we drew the circuit, we showed that we say the conventional current, they flow from positive. This is conventional current. While electrons, they flow from negative to the positive. Okay? So let's move on. Now, alternating current. Alternating current, they come from main electricity and generator. The main one, the electricity that is being supplied to your home by the government. Okay, they are usually alternating current. The one from Tenaga National, or the one from, depending on the electricity company in your country. Okay, depending on the electricity company in your country. So they give what we call the alternating current. They give what we call the alternating current. Is that okay? They usually from the main electricity supply company of any country, and they generate also. Most generators, they give alternating current. Okay, alternating current is needed for using the transformer, because transformer don't use direct current. Okay, alternating current is what we need for transformer. Transformer do not take direct current, because why? We've explained this. Transformer need to produce a changing magnetic field so that it can be linked from the primary side to the secondary side of the transformer. Transformer, if you put a direct current, it will not produce a changing magnetic field. We need to produce changing magnetic field so that it can be linked from the primary side from the primary coil side of the transformer to be linked through soft iron core to the secondary side of the transformer. That's why we need alternating current for transformer. And that's why the main electricity supply from your countries, they use the AC current. That's why they use the AC current, because they use transformer to boost and transmit the voltage from one location to another. Right? So we've covered this in the high voltage transmission and in transformer and in generator studies. So we say alternating current is needed for use in transformer in national grid. We've done this already, right? Now the direction of the electron flow changes direction regularly. The direction of electron flow normally change regularly. A typical frequency for the reversal of AC current in the main electricity is 50. We've done this in our previous class when we took on transformer. Most countries we say they use 50 Hz as the frequency of transmission. When we put transformer as an electromagnetic device that can step down or step up voltages with the operating frequency remaining constant. When we look at transformer and when we study transformer, we said that a transformer was an electromagnetic device that is used for stepping down or stepping up voltages with the operating frequency remaining constant. So when we do that, we say most countries they use the 50 Hz frequency. And countries that use 50 Hz frequency, the voltage they supply to our home is 230 volts. It's 230 volts. So you can find this question in the multiple choice. Okay? So the main transformer or the main electricity supply to our home is what frequency and what volt. So if you see 50 frequency, the voltage that goes between must be 230. If you see 60 volts, if you see 60 Hz, the voltage is 110. So you must know when 110 volts is being supplied. All countries that use 110 volts, what is their frequency? So you must be able to match them. You cannot mix them up. If you mix them up, you miss the question. Okay, here is the electromagnetic effect of AC and DC. Now let's take a look at this two scenario. We say voltage plotted against time, this is what we have. Voltage plotted against time, this is what we have for this one. Voltage plotted against time, this, voltage plotted against. Probably I think they're asking which one, they're asking a question here, which one is which of these graphs shows below represent the change in voltage over time for a simple AC generator. So probably it has both up down. It has both up down. Okay, so this will be the better option. This will be the best option. Okay, out of these four options, because in an AC or this in sorry in an AC generator, we have what we call the alternating current, AC current, which has both the positive terminal and the negative terminal, just like the one we showed just now, right? Just like the one we showed somewhere here, this one, like this one. It has both the positive and it has the negative side. So this option is the best option for this question. Okay, we move on to the next one. Measuring current. How do we measure current? Which device do we use to measure current? You know, current is flowing in a wire. We just see it. It's just flowing in this wire. This is wire. This one is wire. Current flows in a wire, and we just see this is a symbol of a bulb. Okay, probably we would have looked at circuit symbols. This is a bulb. This is a bulb. This is an ammeter. This is an ammeter. Probably let's draw some circuit symbols. Okay, so that we since now we started measuring circuit. You know, I told you for battery, we draw the first cell, we put dot dot dot, we draw another cell. It shows that there are more cells here. Okay, for this battery, it shows there are more cells. Okay, so we can show some circuit symbol, and then we look at the circuit symbol functions, what they do, what each of them does. Okay, so let's start with the simple one, cell. Circuit symbol. So I just write circuit component. Let's just write circuit component. Component and the symbols used in circuit. When you use circuit, let's look at which symbols we use and the function of each of the components in a circuit. We look at their function and their symbol. Before we write the function, we should write the symbols. We draw the symbols, how they look. Each of the terminology we mention it, how they look, and then their functions. Then we look at their functions. So we start with the first one, which is cell. The first one, number one, we say cell. A cell, the symbol is simply one long arm and one short arm. Okay? To provide energy. What it does is to provide energy. So I will just use maybe 110 only energy. Okay? So the second one is battery. Battery is when you put more than one cell together, two or more cells together. Okay, you produce a battery. If you put two or more cells together, you get a battery. We can simply model a battery like this. We can simply model a battery like this. Just two. Okay, simply we can model a battery like this. Or on the other hand, we can show you if it's more than two cells, then we put dots, put some dots, and then we draw the other arms. We're saying this is more than two cells. Okay, this is a battery. Another element we use in the building circuit is bulb. Electrical bulb. The bulb you put in your house. Okay, the symbol is like this. You draw a circle, and then you draw a cross on the circle. Okay? This is a bulb. What is the bulb used to glow to show the voltage, display the voltage, for glowing? Okay? Number 4. What else? We use, what component will we use? Wire. We just use a line to represent a wire. Just use a straight line to represent a wire. Wire is to transmit the current. Okay, it allows the flow of current to it. That's the function. Then 5, we have ammeter. What is ammeter used for? In circuit, to measure current. Ammeter is to measure current. Ammeter is to measure current. And you draw a circle for ammeter, and then you put a capital letter A in the circle. And then you can just show like it continues. Like this. What is ammeter? To measure current. Measure current. Measure current. Okay? Measure the current. There we have its twin sister called the voltmeter. Yeah, okay. Voltmeter. We have a voltmeter. A voltmeter. Okay. A voltmeter. You draw a circle, you draw a V on the circle. That's just a voltmeter. What do you use a voltmeter for? Also for measuring something. What is that thing we use it to measure? What do you use a voltmeter for? To measure voltage. Measure voltage. Voltage is PD, to measure the PD across the component. The PD across component. Okay? Measure the PD or voltage. Measure the VT, the PD or voltage. That's what we use the voltmeter for. But nowadays we use digital multimeter. The digital multimeter has ability to measure current and voltage. So it's now like one device. I even measure resistance. Okay? Then we have ohm meter. Ohm meter for measuring resistance. Okay? For measuring resistance. Same. For measuring resistance. Okay, we have a switch. Switch, there are two types. We have the open switch and the closed switch. So we show two symbols. We have open switch, and then we have the closed switch. This or this. So open switch or closed switch. Then we have a resistor. Another symbol we use is a resistor. The symbol has changed. It used to be something different. Now the symbol is just this. We didn't measure the function of the switch to open and close the circuit to allow current to flow in the circuit. That's a switch. This is the symbol of a resistor. Resistor is to oppose the flow of current, to reduce it, to draw it back, to oppose the flow of current. If you don't have a resistor, maybe current may be too much and may burn your other devices. So resistor is to slow down the flow of current. Okay? Resistor is to oppose the flow of current. Then which other device do we use? A thermistor. Have you heard of thermistor? Thermistor. And after this variable resistor. Thermistor. They are all class of resistor. A thermistor. Then we have variable resistors or Either you call it variable resistor or you call it a rheostat. Variable resistor. A variable resistor. Or what we call a rheostat. We cross it with an arrow. Just draw an arrow on the resistor. Variable resistor. Or rheostat. So in the exam they may use this name, rheostat. R-H-O, R-H-E-O, rheostat. Okay? A rheostat is a variable resistor. Then we have light dependent resistor. Number 12. We have light dependent resistor. So I'll just write the symbol. Light dependent resistor. LDR. Meaning you draw a resistor. If you look at all of them, they are all types of resistors. This one you see light is falling on it. You show an arrow to so that light is falling on it. This is a light dependent resistor. Okay? We have a diode. What is this used for? For producing opposite. All the resistors have to oppose the flow of current. Okay? Then we have a diode. Diode allows current to flow in one direction only. Diode, the function is to allow the current to flow in one direction. So the symbol. We also have light dependent diode or light emitting diode. Light emitting diode. This is a diode. They allow current to flow in one direction only. Current cannot flow in the reverse. Current will pass through a diode in one direction. Okay? It allows, if you don't want current to reverse, you use a diode when you're building a circuit. If you don't want current to flow backward, just like Almighty God, Allah use a valve in the vein so that the blood do not flow down, it only goes in one direction. So in we as human beings, we model the valve in the circulatory system. We use that to model a valve, okay, in circuit, in electrical energy, to allow current to flow in one direction, so the current do not reverse, okay, and so on and so forth. So if you remember anyone who come here and add it to it, there are many, okay. This is not all, but let's move on so that we can do the work for today. We're just showing you the symbols that you need. So this is a battery. So a simple circuit. If you want to measure the current in a circuit, what do you do? Like we said, this is the bulb. When the current reaches the bulb glows. It will glow. It will light up. The bulb will light up, and then you see the bulb. The whole place will bright up. That's because current has flowed into this bulb. This bulb is a form of resistance. Provide resistance. So how do you know the amount of current that is flowing in the wire? We connect the wire to one terminal, the positive terminal, and the other side of the wire to the negative terminal of the ammeter. We connect one side of the wire to one terminal of the ammeter, the positive terminal. We connect the other side of the wire to another terminal of the ammeter. Well, when we do that, the amount of current flowing in this wire will be displayed on the ammeter. Okay? The amount of the amount of current that is flowing on this wire will be displayed on the ammeter. So we say ammeter is used for measuring current in a circuit. And remember, we connect it in series with the wire. Everything is series, like it's one straight loop, one straight line, not multiple loop. Okay? When you do another loop, that would be a parallel connection. So when we are measuring current, we connect the wire to the ammeter in series. in series. In series. This is different from voltage. When we are measuring the voltage or the PD across this bulb, we have to connect the voltmeter in parallel to this bulb. Maybe we're going to reach there. We connect the voltmeter parallel to this bulb. What I mean is that, let's show it classically. If this is our circuit, let's say this is our circuit, and we have this bulb, we have this bulb, here we connect the ammeter in series. You see, in series, meaning it's on the same loop. On the same loop, we connect the ammeter here. We put the ammeter here. It's in series with the bulb. This is the bulb. It's in series with the bulb. The ammeter is in series with the bulb. Okay? It's in series with this bulb. So this will measure the current for you. This will measure the current. This one will display the value. You know how ammeter looks, right? Ammeter is something like this. You see the value will be displaying here. The pointer is here. Maybe the value here is 0, 1, 2, 3, like that. So if the pointer is pointing to 3, meaning the current flowing in this wire is 3 ampere, meaning the current is 3 ampere. Okay, so that's after that. If I want to measure the voltage, now we talked about current. If we want to measure the voltage across this bulb, what we do is that we connect a voltmeter parallel, you see, from here, we connect the voltmeter and we make it parallel to the bulb. We make the voltmeter parallel to the bulb. We put a voltmeter here. So we create 2 terminals on this wire and we connect the voltmeter parallel to the bulb. This is parallel connection because this voltmeter and this bulb, they are parallel to each other. This is not series. Series is when some things are on the same straight line. Even if not same straight line, like on the same loop. If things are on the same loop, then we can say they are in series. This and this are in series. But this and this, there are 3 loops here now. The first loop here and this second small loop here. So these ones, they are now parallel to each other. They are parallel to each other. Okay? The voltmeter and the bulb are parallel to each other. This is how we measure voltage. If I want to measure the voltage or the EMF in the battery, I must connect a voltmeter parallel to this place, parallel to the battery. So any device or component you want to measure the voltmeter, you must measure the voltage, you must connect the voltmeter parallel to that component. Any component in the circuit, whether it's filament lamp, fluorescent lamp, a bulb, a battery, a cell, you must connect a voltmeter parallel to that device or that component. But ammeter, no. Ammeter, it measures current. We just make it in series with that. We just make it on the same series with that, with the bulb or with the device that you mentioned. Okay, I hope that is clear enough. Now let's move on. So here is the question. The diagram below shows an electric circuit containing 3 meters. Containing 3 meters, all connected correctly in the boxes provided. Identify the ammeter. Ammeter are always in series with the resistor or with the bulb. Okay? Ammeters are always in series. So the correct ammeters are these 2 boxes. Right? This third box is for voltmeter, to measure the voltage across this resistor. To measure the voltage across this resistor. So this one is not for ammeter. But this and this are for ammeter. Is that okay? So we move on. Now let's take a look at ammeter, like what I said they look like. Analog, this is the analog one. We have 2 types of ammeter. We have the digital one, which does not, it will just show you the value. It's just like when you press a calculator, it just gives you a value. The digital one gives you a value, but the analog one, you have to read it yourself. If you connect this one terminal to one side of the wire, let's say to this side of the wire, and the other terminal to this side of the wire, it will give you to display the value of the current that is flowing. You will read by yourself. This is about 2.8 or 2.7 ampere. So you can see here the value displayed here is about 2.7 or 2.8 ampere. Is that okay? From this analog ammeter. So for this digital ammeter, it just gives you the value straight away. You don't have to start reading. It gives you the value straight away. But we know one of the experimental things to take care is to avoid error due to parallax. Always avoid error due to parallax. Meaning you must, your eye level, your line of sight, from your eye to the calibration on the ammeter must be on the straight line. You cannot be in a corner or in diagonal and try to read the values. So you must avoid error due to parallax. And you must avoid the zero errors. Okay, there are two errors you can get here, the zero errors and the error due to parallax. Now for the digital meter, it just gives you the value of the current. Once you connect it to the wire on both sides, it just gives you the value. This one you don't need to read. So you know this is at 0.17 ampere. So the digital multimeter or the digital meter is way better than the analog one. The analog one we have to read. But in science, in physics lab, we normally have more of the analog one for teaching purposes. Okay? So that you learn how to read meter. Okay, so that's that for meter that's used for measuring current. Now electrical conduction in metals. How is electricity how is it being conducted in metals? Remember we said metal has a charge and electron, a delocalized electron, a free mobile electron that is free to move. That's why metal is a conductor, because the electrons are free to move. The electrons in metals are delocalized, they're mobile, so they're able to move. That's why you see that they have an arrow on them. They have arrow, a line and an arrow, the electron. But if you look at the charge, they're just in one place. But the electrons are able to move. So that's why we say the metal ions. Okay, the metal ions are in one place, while the electrons are able to move. So metals, because they have free mobile electrons or delocalized electrons, then they are able to conduct electricity. They are able to conduct electricity. They have electrons that move. Okay? We say conventional current. I already explained this. We say conventional current flows from the positive terminal of the battery towards the negative one. While electrons, they flow from negative. See, electrons move from the negative. We showed this earlier on. Electrons, they flow from the negative to the positive. While conventional current, they're coming from the positive, okay, to the negative. They're coming from the positive to the negative. Take note, they will confuse you in the exam and they will give you this. Conventional current. Electrons are negatively charged. This means that the electrons flow from the negative to the positive. Electrons, they flow from negative terminal of the battery to the positive terminal of the battery. But conventional current, they are flowing from the positive terminal towards the negative terminal. Is that okay? Okay, so that's for this first part.